Among our list of basic functions, the inverse trig functions are some of the only remaining ones whose derivatives we have left to compute. It turns out that implicit differentiation and some knowledge of trig identities allows us to compute these derivatives quite easily. For example, let's try to compute the derivative of the arcsine function. To begin, let's first just recall some conventions, such as the fact that conventionally, the domain of arcsine is taken to be the closed interval from -1 to 1, and its range is typically taken to be -π/2 to π/2. In addition, writing arcsine of y equals x means that x is the angle that produces the vertical component of y. In other words, the function arcsine takes in vertical components between -1 and 1 and produces the corresponding angle along the unit circle that achieves them. The convention that the angle be between -π/2 and π/2 means that we're taking the angle on the right-hand side of the unit circle. Let's write f of y for the arcsine function f of y equals arcsine of y. Because f is the inverse of sine, we have the relationship sine applied to f of y equals y for each y between -1 and 1. To find the derivative of f then, we can differentiate this identity on both sides with respect to y. On the left, we'll use chain rule. Since the derivative of sine is cosine, we obtain a derivative of cosine applied to f of y times the derivative of f. On the right, we just get 1. At this point, we recognize it's possible to solve for f prime of y, and we get f prime of y equals 1 over cosine applied to f of y, or 1 over cosine applied to arcsine of y. Now, this expression of f prime is okay, but it might be possible to simplify it further. Indeed, arcsine is the inverse of sine, so maybe there's a neat relationship that allows us to express the quantity cosine of arcsine of y in a more straightforward manner. Thinking in terms of the relevant triangles, let's write x for the angle given by arcsine of y. As we said earlier, this is the angle that achieves the vertical component of y, so upon dropping a leg of a right triangle, we find that this dropped leg has length y. The hypotenuse of this triangle is just 1, since the triangle sits inside the unit circle, and this allows us to write the other leg as the square root of 1 minus y squared. The expression we're interested in is cosine of arcsine of y, or, since x equals arcsine of y, cosine of x. But cosine of x is just the length of the lower leg of the triangle, which is the square root of 1 minus y squared. In total, then, we find that cosine of arcsine of y equals the square root of 1 minus y squared. Putting this into our expression of the derivative, we find that the derivative of arcsine of y is equal to 1 over the square root of 1 minus y squared. The derivative of the other inverse trig functions can be found in a similar way. We've listed all of the derivatives in a table here. One thing to note is that the derivatives come in pairs, where the version of the inverse trig function that has a co in front of it has a minus sign in front of its derivative, in a similar way to that of the derivatives of the ordinary trig functions. Our final result deals with inverse functions more generally. Let's suppose that f and g are inverses to one another, meaning that, for example, f applied to g applied to y equals y for each y in the domain of g. And suppose that we know the derivative of f at some point x naught, that is, we know the value f prime of x naught. The question we'd like to answer is whether it's possible to determine what the value of the derivative of g should be at the corresponding point y naught equals f of x naught. To find this derivative, we'll use implicit differentiation. Specifically, we'll differentiate the relation f applied to g applied to y equals y with respect to the variable y. On the left, we'll use chain rule to get a derivative of f prime applied to g of y times the derivative of g, and on the right, the derivative is just 1. Isolating g prime of y then, we find that g prime of y equals 1 over f prime applied to g of y. At the point y naught, we have g of y naught equals x naught, and so we get the relation g prime at y naught equals 1 over f prime at x naught. In other words, the derivative of the inverse function is in some sense the reciprocal of the derivative of the function. The only subtlety is that the point at which the reciprocal is evaluated is the point x naught, which corresponds to the point y naught in the domain of the inverse function g.